All right. Our first session today is real-time integration with Synergex's streaming platform. As I mentioned, Steve is a solutions architect in our professional services team. Steve joined Synergex in 1997 and has spent decades working with customers to help them maximize their vertical market software applications. As a solutions architect, he offers deep expertise in many tools and technologies, making him a valued partner to our customers. Most recently, Steve has become an expert in Synergex's streaming integration platform, guiding customers towards scalable distributed architectures. Steve is going to share how this platform enables high performance, real time data replication, paving the way to modernization and cloud migration.
Hi, good morning. My name's Steve Ives, and I work for the Professional Services Group here at Synergex. I'm here today to talk to you about our new streaming integration platform product. The streaming integration platform is a new offering from Synergex designed to provide a new way to integrate Synergy applications with others in your environment. Designed with performance and high availability as goals, it provides a new way to expose your application data in near real time reliably. Over time, the streaming integration platform will likely be extended to target a variety of environments, but at launch there will be two, which result in the replication of data to remote SDMS files on other Windows or Linux systems and to Microsoft SQL Server databases. As I mentioned, over time there are likely to be many more and other ways to leverage the platform. For example, we've already begun to consider targeting environments such as Delta Lake, but the possibilities extend far beyond that. And this isn't just an early proof of concept. We're already starting to deliver the streaming integration platform to several customers, and without mentioning any names, I'll explain some of the initial use cases later in my presentation. By the way, this is not another open source do-it-yourself project. The streaming integration platform is a fully supported product suite from Synergex. A streaming integration platform deployment typically involves several network nodes, often running different operating systems. There are three general categories of systems involved. Origin systems are those that host the original DBL application and its data, and represent the single source of truth in the environment. Intermediate systems are those involved in the transportation and storage of various types of messages, including CDC messages describing every change that your application makes to its data, and snapshots that represent a copy of the data at a specific point in time. And finally, target systems are the final recipients of that replicated data set in some form. We've designed the streaming integration platform to be usable from virtually any Synergy environment, allowing both Windows and Linux to serve as origin and target systems, and OpenVMS IA64 or Integrity systems to also function as origin systems. It may be possible to support some streaming integration platform components on IBM AIX in the future, although we've not yet attempted to do so. Unfortunately, OpenVMS on the Alpha AXP platform is much less likely to be supportable due to several missing dependencies on that platform. The architecture is highly flexible, using custom agents for each target type. In the future, we can add new target types by developing a new agent to support that type of deployment. And if necessary, third parties could also extend the environment to support new targets by creating their own agents. The streaming integration platform is internally complex, involving a wide range of products, libraries, and protocols. However, we've chosen carefully, aligning with industry standards and industry standard protocols such as Kafka for messaging and S3 for bulk data storage. I've mentioned Kafka a couple of times now, but some of you may not have run across it before. So let me take just a couple of minutes to explain what it is. Apache Kafka is a distributed environment or a distributed event streaming platform, more accurately, that reliably publishes, stores, and processes high throughput, real-time data streams at scale. Think of it as a high-speed postal service for data inside your organization. Imagine your applications and systems are constantly generating letters. Every transaction, every file update, every event is a new piece of mail. Traditionally, getting those letters delivered to all the right places quickly and reliably has been very difficult. Kafka was designed to solve that problem. It's a distributed platform for handling streams of events in real time. What that means is that instead of delivering letters one by one, Kafka acts more like a mail hub or a sorting office, where everything gets stored safely and can be picked up by whoever needs it whenever they need it. It guarantees that the letters arrive in the same order that they were sent, and it allows multiple recipients, different applications, databases, or services to read the same data independently at their own pace. In simple terms, Kafka enables you to capture a continuous stream of information from one system and reliably share it with multiple other systems. It was initially built by LinkedIn around the 2010 timeframe to handle their massive activity feeds, and then it was open sourced by them in 2011 through the Apache Software Foundation. Today, it's used by thousands of companies worldwide. Some companies use it to process financial transactions in real time, others to monitor fleets of connected devices, or to feed analytics and AI systems. For us, Kafka and its modern alternative, Red Panda, is the backbone of our streaming integration platform, as it provides the reliability, scale, and flexibility that we need to replicate Synergy data into various modern targets. Let's briefly take a step back and think about data replication, because for some of you, this is not a new concept. In 2008, Synergex introduced SQL replication as a method to replicate a DBL application's data and changes to that data into a SQL Server database in near to real time in most cases. The SQL replication environment wasn't launched as a product, however. Instead, it was an open source reference implementation that demonstrated how to replicate your data to a SQL Server database. The solution relied heavily on code generation of SQL connection API code in particular, and relied heavily on the use of DBL's I/O hooks to detect and process change events. It also utilized an ISAM file as a non-persistent transaction log. Since that time, the SQL replication solution has been implemented by many customers, some of whom have built their own solutions, while others have been assisted by our professional services team. The solution could be very effective, but was far from perfect, with perhaps the primary area of concern being that non-persistent ISAM file used as a transaction log. The streaming integration platform shares some similarities with the earlier SQL replication solution. It continues to leverage DBL's I/O hooks to intercept and process your application's I/O operations, but rather than writing CDC information directly to a local queue file, those events are routed through a local message broker application. The primary role of the message broker is to guarantee the delivery of those messages to the Kafka environment, which operates on different network servers. A second application, an agent, is then responsible for retrieving those change event messages from Kafka and implementing the necessary change in the targeted data store. That data store could be a SQL Server database, could be an SDMS data file on some other system, or something else in the future. The SQL replication solution can still offer a great solution, especially in smaller environments, but the streaming integration platform takes things to a whole new level in terms of significantly improved throughput and resilience, thanks to its persistent transaction log, the opportunity to support multiple consumers receiving and processing the data, and supporting many more targets in the future. This slide effectively summarizes some of the benefits of using the streaming integration platform compared to other earlier solutions. As I've already mentioned, the persistent transaction log provided by Kafka is a significant development in many ways, not least of which is that it inherently supports the ability to have multiple independent consumers of the information, each targeting different data stores or other use cases. While initial support will be limited to replication to Microsoft SQL Server and Synergy SDMS databases, there are numerous opportunities to expand support to a wide range of target environments in the future, some of which are outlined on this slide. From the outset, we've paid close attention to both performance and resilience. Although every use case is different, the testing that we've done so far has demonstrated significantly higher rates of throughput compared to other earlier solutions. Although not part of our initial product offering, the base environment has been designed with future transactional support in mind, and we do expect to announce support for fully transactional capabilities in the future. As I mentioned earlier, the streaming integration platform comprises several parts that collectively deliver the overall solution, as illustrated on this slide. I wanted to just take a couple of minutes to highlight some of the more important components and make sure that you know what each one does. The I/O hooks are probably the simplest component and the most familiar to many of you. First introduced in DBL version 10, which it's hard to believe was released almost 13 years ago, I/O hooks provide an effective way to intercept and take action whenever your application changes its data. I/O hooks are at the foundation of both SQL replication and the streaming integration platform. As I mentioned briefly earlier, there is a message broker application that runs locally on the same system as your DBL application. Its job is to receive the messages generated by the I/O hooks running in your application's user processes and quickly and reliably forward those messages to the Kafka environment. Kafka itself is the message store, essentially, the persistent transaction log. It typically resides on Linux, often in a cluster of 3 or more nodes. More on that later. There's also an application called the Snapshot Agent. It's another application that operates on the same system as your DBL application. Its job is to, on request, produce a snapshot of your entire dataset, or at least the part of the dataset that you choose to replicate, and upload that snapshot to some network storage server, typically using the S3 protocol. However, other protocols can be used if necessary. I'll explain snapshots in a little more detail shortly. Then we have perhaps the most important piece of the puzzle, the replication agents. A replicator agent is an application that runs on the target system, usually. They are primarily responsible for 2 tasks: populating the target data store initially, and then keeping that data store up to date as changes are made by the origin system and those messages stream into the Kafka transaction log. And finally, the configuration server. This is an optional component that can be used to centralize and simplify the management of configuration settings required by all the other components. It can also be used to perform centralized management of TLS certificates, used to implement secure network communications between the various other elements of the solution. Let's talk about the engine that makes this whole platform possible. Many people in the industry know Apache Kafka. It's the original event streaming platform, powerful, proven, battle-tested, but it does come with some baggage. Kafka is written in Java, and while Java is portable, it comes with a lot of overhead typically. That means that you often need to tune the system aggressively to achieve high throughput. Apache Kafka also relies on a product called Zookeeper, a separate coordination service which adds complexity to the setup and management of an Apache Kafka environment. And when you're trying to run it at scale, that complexity translates into real cost in time, hardware, and operational overhead. Now let's contrast that with something called Redpanda. Redpanda is a drop-in replacement for Apache Kafka. It's designed much more recently and designed with modern hardware in mind. Redpanda is written in C++, which allows it to run much closer to the metal, far more efficiently and with dramatically lower latency. It's optimized for NVMe and NVMe storage and multi-core CPUs, so it squeezes the absolute maximum out of today's servers. Importantly, it's fully Kafka API compatible. That means that you don't have to change any client code. Everything built for Apache Kafka will work with Redpanda. The result? Redpanda delivers orders of magnitude better performance. We're talking millions of messages per second, with latencies measured in microseconds, not milliseconds. It has a simpler architecture. No Zookeeper is required. It's a completely standalone implementation in its own right. There are fewer moving parts. It's easier to deploy and easier to operate. And because it's more efficient, you typically need fewer servers to do the same job, which reduces infrastructure cost. So while Kafka is the household name that we all refer to, Redpanda is the better choice for modern workloads. It provides us with all the benefits of the Kafka ecosystem, compatibility and resilience, but with improved performance, reduced complexity, and lower costs. One thing to note, whether you use Kafka or Redpanda to achieve production-grade fault tolerance, you need at least a 3-node Linux cluster. But with Redpanda, you'll often find that those 3 nodes can handle the workloads that might take 5 or more nodes when running Apache Kafka. This slide is for those who want to peek under the covers and see how things actually work. We start with an origin application, an original DBL application, as shown in the upper left corner of this slide. And we're already demonstrating that the I/O hooks have been added to the mix. By the way, thanks to global I/O hooks in later versions of Synergy, adding I/O hooks to the application, to your application, can often be achieved with no changes to your actual underlying code. When a data change event is captured by the I/O hooks, code in the hooks sends a message to the message broker application running on the same system. By the way, in the case of an OpenVMS cluster, there will be a message broker on each cluster node, but only one will be active at any time, ensuring first in, first out delivery. As shown, the message broker sends the message to Kafka, specifically into a Kafka topic. We call this the CDC topic, or the change data capture topic. It's not strictly accurate, but you can think of a topic as being a persistent queue. Once a CDC message has been delivered into the CDC topic, it will be collected and processed by agents. In this case, we see the SQL agent collecting and then processing the message, replicating the same change that occurred in the origin application, but this time affecting a row in a SQL Server database. As I mentioned earlier, the CDC topic can be monitored and processed by multiple agent applications at the same time, each of which independently maintains its own current position or offset within that topic of streamed messages. So here, each change that occurs in the origin data store is applied, usually almost immediately, to one or more other data stores. By the way, when I was describing the infrastructure earlier, I talked about systems, Linux, Windows, OpenVMS systems, for example. But an agent might not run on a traditional system. It could be that, for example, an instance of, say, the ISAM agent could be running inside a Linux Docker container managed as part of a Kubernetes cluster, being perhaps dedicated to some kind of specific data processing task. The opportunities are really endless. Here we see yet another agent processing events from the same CDC topic. This could be another instance of the ISAM or SQL agent fulfilling some slightly different role, or perhaps something else in the future. What I want to do here is to use this agent to show you what happens when a brand new target node is first started, and currently has no data whatsoever, be that ISAM files or be that SQL Server database or something else. That node needs hydrating with an initial copy of the entire dataset, or at least the part of the dataset needed for whatever the use case that node is intended to support. Now, the scenario I'm about to walk you through is not entirely accurate, but bear with me. I'll explain what I mean very soon. When an agent is started for the first time and needs to be hydrated with initial data, this process occurs via a mechanism called snapshotting. We see the agent sending a request to a different topic in Kafka, this time a topic called the snapshot request topic. Essentially, it's saying, hey, someone out there, I need initial data. Enter the next component that we mentioned, the snapshot agent, which will receive that request. It monitors and constantly looks at the request topic, and it will respond by preparing a snapshot of the entire replicated dataset of the application. Depending on the number of files involved and the size and number of records in those files, the creation of the snapshot can take a while. But once complete, the snapshot is then uploaded to the network storage. By the way, the snapshot data is highly compressed. The overall size of a snapshot typically is a small percentage of the overall initial size of the dataset. As soon as the as soon as the snapshot has been uploaded, the snapshot agent sends a message back to a third Kafka topic, the snapshot response topic, indicating that the snapshot is available. As soon as that message is posted, it will be received by the original agent that requested the snapshot in the first place. And the final operation involves that requesting agent applying the snapshot data to its target data store. The exact mechanism used depends on the client. The ISAM client downloads and expands the data before fast loading the data into local SDMS data files. The SQL agent is able to stream the data directly from the S3 storage directly into the target SQL Server database tables. I wanted you to see the underlying or understand the entire process before I explained how things typically work in a real-life scenario. In reality, it's going to be undesirable and unlikely for any particular agent to have to wait for a snapshot to be created and uploaded. What generally happens is that an initial snapshot will be artificially created through management tools as part of the initialization of the whole environment, and before any agents are started for the first time. And there will be a corresponding entry in the snapshot response topic. So before an agent requests a new snapshot, it will first check the existing snapshot response topic and determine if there is an existing snapshot that can be used. It will then immediately, if there is a snapshot, and generally there will be, it will immediately then be able to start downloading and hydrating its data store fairly quickly. The metadata for each snapshot also indicates the offset in the main CDC topic that corresponds to the point in time that the snapshot was taken. So having restored the latest available snapshot, the agent can position to the appropriate place in the CDC topic, process the CDC messages that have occurred since the snapshot was taken, and the data set is thus hydrated fairly quickly and brought bang up to date. By routinely creating new snapshots regularly, weekly, or perhaps more frequently, it becomes easy to hydrate new nodes with minimal delay. As I've mentioned several times now, we will initially provide two replication agents, one for replicating to remote SDMS files on other systems, and the other to replicate to Microsoft SQL Server databases. Both of those agents are built using Microsoft.NET, currently .NET 8, and can therefore be deployed on either Windows or Linux systems. The ideal scenario for optimal performance is to deploy the agent on the same system as its target data store. Each agent includes a built-in browser-based user interface that can be used for monitoring and management purposes, allowing you to view log files and other relevant information. Each agent also exposes a REST API that can be used for remote management from custom applications and custom workflows. Both the user interface and REST APIs, of course, require authentication before any administrative functions can be used. Another component is the configuration server, which can optionally be used to simplify two aspects of the final deployment: centralizing configuration management and TLS certificate management. All individual components rely on configuration data to determine the environment in which they operate. While all support the use of local configuration files, it's essential to remember that the tools frequently operate on different network systems, often under different operating systems. This means that performing an initial configuration or making subsequent configuration changes can require administrators to log into multiple systems and edit multiple configuration files, and must ensure that everything matches exactly between the different systems in the configuration. With the configuration server in place, configuration of the entire environment can be centralized. And because some of the components have browser-based user interfaces and offer RESTful management APIs, they of course require TLS certificates to support secure HTTPS communication. You can, of course, elect to provide your own publicly trusted certificates from an external CA, or indeed provide your own self-signed certificates if you already have the necessary infrastructure in place. But another option is to use the configuration server's built-in ability to generate self-signed certificates for you for this environment. When you install the configuration server, it generates a new certification authority and then uses that CA to generate a TLS certificate for use by itself. The other tools that require TLS certificates, right now the ISAM agent and SQL agent, have also the built-in ability to request and download and use a certificate from the configuration server. The config server is currently supported by both the ISAM and SQL agent applications, both for configuration and TLS certificate management, and we plan to add support for centralized configuration management to all of the other tools, the message broker, the snapshot agent, and so on, in the near future. The config server itself is also a .NET application, currently .NET 8, and as such it can be deployed on any suitable Windows or Linux system. Well, that's an overview of the streaming integration platform. But before I show you a demonstration, I'd like to describe some of the initial customer use cases that we're working through with the first few customers who intend to use the products, but no names will be mentioned. The first use case is that of a customer operating a national business where their DBL application is the core business system. An OpenVMS Integrity or IA64 cluster hosts the applications. The data is stored in RMS ISAM and relative files, with numerous integrations with other applications and platforms already in place. In this case, the customer's goal is to migrate the core application from OpenVMS to Linux over time, with the ultimate goal of hosting it in the AWS cloud. The plan involves using the streaming integration platform to replicate the current OpenVMS RMS data to SDMS data files on Linux. With that in place, the next phase will be to migrate read-only application workloads, such as reporting and data extract operations, from OpenVMS to Linux, operating on the replicated dataset. At the same time, work will be done to remove any OpenVMS-specific dependencies from the remaining codebase, ultimately allowing all workloads to be migrated from OpenVMS to Linux. At that point, the OpenVMS cluster will be decommissioned. Work on this project has been underway for some time, with activities progressing as planned. And also, we're in discussions with two other OpenVMS customers, both of which have very similar challenges and very similar goals. So we might see this replicated in a couple of other instances fairly quickly as well. The second case study is somewhat different. this time involving a customer who's been using the original SQL replication solution for several years and is looking to improve the resilience and throughput of their environments as their company and operations continue to grow. The customer is a large privately held organization that has enjoyed significant growth in recent years, and that growth is expected to continue. Again, the company's primary line of business application is a DBL application, with its data stored in SDMS databases. The host system, Linux in this case, currently supports over 7,000 concurrent interactive users, most of whom enter and manage orders via the retail point-of-sale applications. As you can imagine, the volume of data processed daily in this environment is fairly large. Their current SQL replication environment replicates data from approximately 90 primary SDMS files to a SQL Server database, which is then utilized to support a wide range of other applications and workflows. Harmony Core is also used in this environment, amongst other things providing a robust mechanism for different applications to send updates back into the system of record as necessary. The plan involves migrating from traditional SQL replication to SQL replication using the streaming integration platform to achieve higher levels of throughput and reliability, as well as supporting new workflows that could be driven directly from the CDC data stream working alongside the SQL agent. This project is kicking off as we speak this week. The third and final use case is not quite as advanced as the previous two, but we hope it will start to gain traction soon. The customer in this case is in the banking and payments industry, and their back-end transaction processing environment runs in traditional DBL on Windows with .NET services layered on top. Once again, this project will involve a phased roadmap. The plan is to first replace the current ISAM-based or file-based queues with Kafka, and then migrate away from a homegrown custom SQL replication infrastructure by introducing the SQL agent. Additionally, it involves replacing legacy services that currently use XF Server Plus with Harmony Core REST APIs. In the long term, there's a desire to migrate from traditional Synergy to .NET, and from Windows hosting to Linux, and eventually perhaps even to containerized services. I just want to take a moment to mention Harmony Core, our web services framework, which remains a key component in many integration scenarios. As with the additional SQL replication solution, the streaming integration platform replicates data in one direction from the origin system and the source of truth and out to read-only replicas that can be used for many use cases. Some of those use cases may well require a two-way flow of information, i.e. the ability to send updates into the system of record from external sources. For DBL applications, Harmony Core is absolutely the correct way to satisfy that need. In addition to its ability to expose queryable data in OData protocols, its ability to easily expose RESTful web service endpoints that allow you to expose business functionality in a controlled, monitored way and safely, combined with the fact that RESTful APIs can be easily called from pretty much any other software environment, really does make it a compelling solution. If you need a reliable and scalable bidirectional solution, then combining the streaming integration platform with Harmony Core RESTful web APIs is the answer. Enough of the slides, let's see a demonstration showing the agents in action and data flowing through the system. After the demo, I'll open the floor for questions. Okay, let's show you the streaming integration platform in action. What I'm going to be doing is replicating two sample Windows ISAM files to a local SQL Server database. This is the SQL Server Management Studio. You can see that I have already got a database created called Kafka Replication, and that database does not have any user tables in the database. It's essentially completely empty. One of the two files in our sample environment is tiny. It only has 8 records. The other is a little larger. It has 100,000 records. We'll be running the snapshot agent, message broker, and SQL agent all on my local Windows development system. I also have Red Panda and a MinIO S3 server running in a Linux virtual machine, also on my laptop. No snapshots have been created yet, so the S3 bucket in MinIO is currently empty. Background services don't demo well, so what I'm going to be doing is using a little desktop application that we call Launchpad to host the demonstration. Launchpad is a tool for developers to use. You won't normally see this in use in the environment. When we first launch the SQL agent, it's going to take a few seconds before its UI becomes available for it to get fully started, by which time the snapshot will already have been prepared, uploaded to the S3 server, and streamed into the database. It all happens really very quickly with this small data set, but I'll show you some more stuff as we go through. Once we have the data replicated, we're also going to use another developer tool to generate some random I/O to the larger of the two files, the employee file, and we'll see those operations being reflected into the database. So we've already seen in SSMS that we have our database and it's currently empty, and here we are in Launchpad. I'm going to turn off the ISAM agent console because we're not going to be using the ISAM agent in this demonstration to replicate to ISAM. We're just going to be using the SQL agent to replicate to SQL. So in this area of the screen, this is the SQL, or you're going to see the SQL agent's console log messages, essentially. From here, we'll see output coming out of the snapshot agent. And over here, when we actually start generating some activity on the file, this is basically the message broker, where we'll see messages coming up from the message broker. In some cases, the logging has been cranked up a little to make it a little bit more verbose for demo purposes. You won't necessarily see all of these messages that we're going to see in a real production environment. Let's also go off and view our Red Panda environment. So if I open our Red Panda console, this is Red Panda's. This is a management tool that you can use to view information about a Red Panda environment. And basically in here, you will see that we have 3 topics. You can think of each of these topics, like I said earlier, as kind of a queue. That's not strictly what they are, but essentially think of it like that. Default replicator is going to be our change data capture topic. So as individual creates, updates, and deletes happen to the data files, they will appear as messages in this topic. And then we have 2 additional topics. We have the snapshot request topic. So if an agent needs a snapshot to be created, it will send a message here. The snapshot agent will pick up that message and produce the snapshot, upload it into S3. And when it's finished, it will send a message to this snapshot response topic. So those are the 3 topics in Kafka. We will also be using, as I've mentioned already, MinIO, which is an S3 server. So let's go and look at what state MinIO is in right now. Let me just log in. And in MinIO, these are what are called buckets in the S3 world. So think of it, it's kind of like a folder, but it's actually called a bucket. And in our development bucket, which is where we're going to use it, well, what we're going to use in this environment, there's currently nothing in it. So it's just an empty bucket, an empty folder, essentially. And we'll see that change as we go through later as well. Okay, let's get some things spun up. So let's go back to Launchpad and let's start up the snapshot agent so that it's ready to go. So this is just launching a background process and capturing its console output so that we can see what's going on. Not much comes out of the snapshot agent at this point, starting Kafka consumer service. So the snapshot agent is basically monitoring that snapshot request topic, waiting for messages to be sent into there. Okay. As we go back to Launchpad, let's also get we're not going to be using it straight away, but we'll get it running. Let's start the message broker. So the message broker, we can see Kafka metadata loaded, starting producer thread. So the message broker, remember, is the one that is called by the I/O hooks on the original DBL system and is responsible for sending those CDC, those change data control or change data capture messages into the default CDC topic. We call that default replicator in this particular configuration. So that's what that's doing. we'll go back to Launchpad. Okay, I think we are about ready to go. Let's go. What shall we do now? Yeah, I think we can set things going. So I'm just going to start the SQL agent. And as it spins up as a background service, again, I'm going to capture its console output and just show it in this log up here. And you can see it's gone into initializing state. It's connected to the database. It's showing us some configuration information. Checking for database for tables, it found that two of its two tables are missing. It's reporting that it's missing these two tables. It's going into restore mode to restore the tables. It's looking in the snapshot response topic to say, is there an existing snapshot I can use? It didn't find one, so it sent a request for a new snapshot, which if we look down in the snapshot agent, you can see that request has been picked up and actioned. So the snapshot agent exported the contents of both of these ISAM files to something called a Parquet file, and we can see each of those Parquet files being uploaded into the S3 storage, and it successfully completed its job, and then sent a message to the snapshot response topic. We'll look at the messages in a moment. And that message was then picked up by the requesting agent, who then went into restore mode and restored the table, department, and employee, and reported that missing tables had been restored twice for some reason. I'll have to look into that a little later. And now it's processing instructions. So it's just sitting there doing nothing right now, just monitoring the CDC, the change data capture topic, waiting for messages to come in to say activities happening in the ISAM file that we need to replicate. So everything's up and running. Yeah, let's go and take a quick look at what the SQL agent UI looks like, because they do have user interfaces, fairly basic, but for management primarily. So let's look at the SQL agent console. This is a ASP.NET application. It does take a few seconds to spin up the very first time you address it, which is what's happening here. And then we get this little view of what's happening in the agent. No damage can be done here. This thing is, it does have the ability to make some changes, but that can only happen when it's in an admin mode. This is everything read only here, so we're just browsing information. And we can see that the agent status is processing, so everything's normal. It hasn't actually done anything yet. It has done it has restored the snapshot. We can see the details of the snapshot here. If you remember that, if you look at that GUID ending C3B8, we'll see that in a moment when we look elsewhere. But it's telling us the snapshot was created at this date and time. It's associated with that offset in the CDC topic, which is 0 because there's nothing in the CDC topic. So this was the very first snapshot before any activity. And it's telling us where the snapshot server is and what bucket the snapshot is located in. This is just information about our Kafka environment. And you can see this page is updating periodically by default every 1 second. We can slow that down if we don't want it to refresh quite so often. Or we can turn it off manual, put it on manual and just refresh it manually when we want to. We can also see various other pieces of information. I'm not going to go through everything here, but if we look at snapshots, we can take a view of what snapshots are out there available to us, and we can see that there's that C3B8. We can drill into that snapshot and get information from the S3 environment. And we can see that that snapshot includes the Parquet files for both the department and the employee file, and we can see the size of those Parquet files. Just over 2 megabytes with 100,000 employee records in. This stuff is highly compressed and great to work with. Another thing we can do is go take a look at the database and what state the database is in. And we can see, I guess I was slightly off on the record count. I must have had some other activity in my file that I'd forgotten about. So we've got a department file. These are the tables in the database. Department and employee both exist, and that's the number of rows currently in the table. And we can see how many columns and how many indexes each of them has. So brief information about those things. Okay, what do we want to do next? Let's go take a look at, just to prove things, let's go look at SSMS again. And if we do a refresh on the database view, we should see that here's our two tables, department and employee. And if we go and select some data from there, SSMS has a little bug going on right now. There's our data, or the first 1,000 rows of 100,000 from the employee table, as you can see. So we have data in the database, and we're ready to get some real replication going. Let's show you restoring an existing snapshot. This is a bit of a contrived scenario, but just so that you can see some things happening. What I'm going to do is I'm going to come back into the agent's UI, and I'm going to put the UI into admin mode, protected by a password, which can be changed in the UI. And now we're in admin mode, and that does enable various other things to happen in this UI. Now we can do some destructive stuff if we have access to this admin mode. So, for example, I've decided that for whatever reason, I want to drop and reload the larger of those two tables, the employee table, for whatever reason, just an admin decision. So I'm going to go to the database, and I'm going to go now to a new option that we have because we're in admin mode, manage tables. And I'm going to, the database management can only be used when the agent is paused, okay? So not processing. So I can pause it here by pressing this pause button, which was also on the main page as well. So now we're not only in admin mode, but the agent is paused from processing. We can pick the table we want to interact with, and in fact, I'm just going to say, let's drop the table. Because this is a destructive operation, we have to do some confirmation to prove that, yes, this is really what we want to do, and it's successfully dropped the table. We should be able to view that. If we go to view tables, we'll see that that table no longer exists. And sure enough, if we go back to SSMS and refresh the data, then sure enough, the table has gone. Okay, let's go back to the agent. What I'm going to do now is I'm going to go back to the status page, and whenever we resume operation, we go through the same checks that we do at startup. So we compare the database to what tables, the tables to what tables we think we should have based on the configuration, and it's going to find that, oh, it's missing a table, so it's going to need to restore it. The difference is that this time there's an existing snapshot. Let's just briefly go back and take a step back and look at what's going on in Kafka. If I go into requests, you'll see here is the request message. That's what the request actually looks like, from the agent to the snapshot agent saying, please make me a Parquet snapshot. And if we go back to the response topic, there's the message that came back from the agent, or the snapshot agent, to the SQL agent saying, okay, your snapshot is ready. Okay. And if we go to MinIO, sure enough, if we refresh the page, we should see there's that same GUID. That's essentially a folder within the bucket. And within that folder, there's our Parquet files that represent the snapshot. What we're about to do right now is say, well, we need a table. But rather than getting a new snapshot, we already have a snapshot that we can use. So we're going to go back to, sorry, I keep flicking around here. We're going to go back to the agent when we resume, it's going to say, oh, I'm missing a table. Look in the snapshot response topic. There is a snapshot I can use. It will restore that table from that snapshot. And then if the CDC topic has moved on, it will replay any changes that have happened to that file, that table, since the snapshot was taken. In this case, that isn't the case, so that won't happen. It all happens fairly quickly. Let's put the let's resume the agent's activity, querying snapshot. So it's looking in Kafka, and then it's saying, yeah, I've got a snapshot. So it looks in S3 and says, well, is it actually there? Yes, it is. So briefly it said restoring table employee, and now we're in processing mode again. And if we go back to view the tables, then sure enough, the table exists again. And again, for those of you who don't believe me, let's go and refresh our view in SSMS. And there's the employee table. Let's select data from the table. There's the bug in SSLS again. And sure enough, we have data in the table again. Almost done. What I want to show you now is some actual replication of change data capture messages happening. So let's go back to Launchpad. I'm going to change up things a little bit. I'm going to dock Launchpad on the left, and then let's dock the agent's UI on the right and go to the status page so we can see what's happening. Right now we've had one operation, which was the snapshot being restored. We've got 0 inserts, 0 updates, and 0 deletes have happened. So what I'm going to do now is use another little development utility that we use that is simply a little program that has IO hooks and opens up the employee file and can randomly do create, update, delete operations to that file. I'm just going to ask it to do one operation to start with. And we'll hit start. And what we're looking for is the message broker should jump to life and say, oh, I've got something to send to Kafka. Send the message to the CDC topic in Kafka. And then the SQL agent should wake up and say, oh, there's a message in the CDC topic. Go grab it and process that same change into the database. And it all happens fairly quickly. So if I run it, we can see there's the message being sent to Kafka. It's already been processed into the database. We've got it was an update operation, and sure enough, if we were to go to the database, figure out which record it was, and look, the data will be updated. Let's do a few more operations. So let's bring that thing back. I like nice round numbers, so let's ask it to do 8 more things, and that will give us a nice even operation count. So again, there's the messages being sent to Kafka. We've now had 10 operations done in the database, and we've had 4 inserts, 3 updates, 2 deletes. Okay, what else do we want to see? Let's go and look what those messages look like in Kafka. So if we go over to our Kafka here and look back at our CDC topic now, here's the messages you can see. We've got a total of 9 messages, plus that restoring of the snapshot, so 10 operations in total. And each one of those messages basically identifies it was an update to this file. And then we've got the unique key for that row that was updated, that record. We have the new state of the data and the original state of the data. So we could figure out net change if we wanted to. In this case, we're not. We're just using the current state. This is just base 64 encoded Synergy records. And, we can obviously decode that and insert it into the database. So each of those messages looks very similar to that. The second one here was a delete. This one is an insert and another insert and so on. It just does random operations. So let's go back to the agent status page. Let's ask it to do a little bit more. Let's ask it to do 90 operations, and we're done, and it's already processed those changes into the database. Let's ask it to do 900. And at this point, my development tools take longer to actually paint the messages into the UI than happens, than it takes to send the messages to Kafka, receive them from Kafka, and make the changes in the database. Just watch how fast this happens. And this is a development system. This is a fraction of the speed of a real production environment. But if I ask it to do those 900 operations, then it's done. Okay. So I think, I think that's my demonstration of the streaming integration platform. I hope that you enjoyed the overview and demonstration of the streaming integration platform, what it is, how it works, and what it enables for you. Now I'd love to hear your questions. Who has the first one?
Thanks, Steve. We're also going to have Jeff join us for this, so he needs to turn his camera on if he's going to be joining us. But while we wait, there he is. Hi, Jeff. As we wait, I am going to gather the questions that you've asked. So thank you, Gordon Ireland, for putting 2 in the chat. Gordon's first question is, can the data managed by Kafka or Redpanda be cleared down periodically, or does it hold everything from the point of switching it on?
That's a good question. And thanks for the question, Gordon. Yeah, typically you're not going to hold everything since the dawn of time in Kafka. You're going to define, and I forget the actual terminology used now, but Kafka topics do have essentially a lifetime or a span of time where those messages will be retained. And typically that will be set to some configuration value depending on what you decide. But typically might be, we're thinking 2 weeks, maybe 3, maybe a month, is the maximum number of change messages you'll store. Clearly, the task is to make sure that at all times you have at least one and hopefully multiple snapshots that also fall within that range. So there's a management task there to make sure that, if you're retaining data for 2 weeks, possibly you need to be making a snapshot at least every 1 week so that you've always got possibly 2 or more that fall within that range. What can never happen is a snapshot. The latest snapshot can never be older than the earliest message in the CDC topic. So that's the way that typically happens.
Gordon had another question, so gold star for Gordon. Does the snapshot use the SDBMS snapshot facility so that even if it takes a few hours to produce, the data is consistent at a point in time?
It does not. The SDMS snapshotting function is very different. All that really does is mark within individual ISAM files a point in time, and you can then subsequently read the data up to that point or from that point or between 2 snapshots or whatever. This is completely separate to that, and we've developed specific tools that are responsible for creating those snapshots. We have 2 versions of those tools, one that runs specifically on OpenVMS and one that runs on Linux and Windows, and they are very high performance tools that allow us to export the data from ISAM files into the appropriate format and upload it to the network storage very quickly. But it's not the traditional Synergy SDMS snapshots.
But you do get the consistency out of out of this mechanism, the same as you would if you were going to pause the whole world, because we're recording everything that happens on the system, and the snapshot knows at what point in the stream of changes it started taking the snapshot and at what point of the stream it stopped taking the snapshot. And it has to replay all of the events that happened between those 2 little goalposts in order to guarantee that it's a completely, like it's exactly at that point in time snapshot.
Yeah.
You can also take snapshots on clean, separate replicated systems that are not receiving any change. So you can build a perfect snapshot that doesn't require a range. It just, you don't do it in the live system.
Okay, next question. What flexibility do you have on the SQL output table? Example is, can we add extra columns like insert date, source database name, etc., for consolidating data across multiple source SDMS databases?
That is not something that we've done to this point at this point in time, but it's certainly something that could be accommodated in the future if there's a demand for that. We are considering, we haven't implemented yet, but we are considering ways of easing some of the typical burdens that we're seeing with traditional SQL replication. For example, adding new columns to a table as a new field appears in an ISAM file, or dynamically resizing the size of a field when something is expanded in the ISAM file. Clearly in DPL, we're now getting the ability to make changes of that nature in real time without affecting the file. And we're looking at ways of rolling that forward into the database. But that, again, has not been implemented just yet.
Okay, last question. So can you quickly drop the emp table? That probably stands for something. Then process the snapshot, and then let us see those after snapshot messages processed to the newly restored snapshot. Curious on seeing this occur, as I believe you mentioned this process will occur after restore.
I cannot show you that right now because the demo was recorded about 2 weeks ago, and I literally am sat at home right now, and I don't have an environment set up. But if whoever you are, if you want to see that happening, we can set up a scenario and demonstrate it. Whenever. Sure.